Hi everyone. So for the last part of this experiment, we need to view Lissajous figures and understand the relationship of phase between two waveforms and also visualize frequency relationship between two waveforms using Lissajous figures. Okay? So Lissajous figures are nothing but XY plots, and the simplest way to understand how a Lissajous figure represents an XY relationship is, suppose this first waveform is x of t and this is of the form say sine omega t. And if you look at the red waveform, this is yt, and since this is 90° ahead of the green waveform, I could say this is sine omega t plus 90°. So essentially there's a phase difference of 90° between the two, and yt is leading xt by 90°. Right? Now xy plot essentially considers the combination of value of signal x and signal y at every time instance and tries to graphically represent it. So suppose the horizontal axis is x, where the amplitude of x goes, and this is y axis. If we look at individual time instances, so for example, if I look at this time instant A, B, C, D, and so on. Okay, so if I look at A, x is equal to 0, y is equal to plus 5. In this case, I have taken both sinusoids to be 5 volt. X is equal to 0 and y is equal to 5. At instant B, x is equal to 5, y is equal to 0. At C, x is equal to 0, y is minus 5. And at D, x is equal to minus 5 and y is equal to 0. Okay. So if we were to look at a single point that represents time and how it traverses, showing the relationship of x versus y, we would notice that it will be like a circle which moves clockwise. When will it be a circle? When the phase difference between the two waveforms is 90°, the amplitudes are identical. Okay? And when will it be a clockwise waveform? When the waveform on the y-axis leads the waveform on the x-axis. If this was the reverse, you would notice a similar structure but counterclockwise. Note that in the previous part, because the amplitudes were same, that is why it was a circle. If amplitudes were not the same, instead of a circle, it would be an ellipse. So how is the xy plot actually made? How do you plot the Lissajous figure or xy plot? So once you have a blank circuit, go to draw and let us take two voltage sources. We can take one terminal sources or two terminal sources in this case because we don't really have to connect them to anything. We just want to use them to display the waveforms across them. So just for simplicity, I'm taking a one terminal AC source. This is one source and this is another source. Both sources have the same frequency, and for the second source, I'm giving a phase shift of 90°. Okay. Now how to decide which one will be x and which one will be y? The one you display first is x, the one you display next is y, and then right click on one of the plots and combine them so that you can very well see the difference. You can also cross check by stopping the waveform and just seeing the one where you did not give phase shift is the one highlighted right now, and the one where you gave the phase shift, the second one, is 90° ahead of the previous signal. So this is the time waveform. On Falstad, if you right click and go to properties and select XY plot, this is what you will observe. Now note that it may look like an ellipse, but this is not an ellipse, because if you look at the extremities, this value is 5 and this value is also 5. So it is just that the scale are not the same. So in order to view the same scale, please undock this scope and click outside. You'll be able to see these endpoints, which you can then use to drag and rescale it so that it looks like a circle. Okay, we will reset the waveform. This is how it looks like. So and you can just click and move it anywhere. You click inside and you can move it anywhere. So what we see here is that based on what we expected, let us also draw these signals again, and I'm combining them, and now I am undocking them so that I can just show them side by side with the XY plot. So this is a clockwise circle because the signal Y is leading by 90 degrees. If I change this now and I made this phase shift to be 0, and of course it became a straight line, and now if I make X to lead by 90 degree, you notice that it is still a circle but moving counterclockwise. Alright. Now if the amplitudes were not the same, say I made the amplitude of the second one to be 3 volt. Let us reset the waveform and see. You notice that the two waveforms are now very clearly differentiable, and now if I look at the scale, this is 5 volt and this is 3 volt, right? So now this is actually an ellipse. The scale is the same, but the Lissajous figure that you get is an ellipse. This is xt and this is yt. So this was all about phase relationship. Just by looking at the shape and the direction of a Lissajous figure, what can be said about the phase between the two waveforms, right? Now we talk about frequency. What we'll do now, suppose the frequency of xt is 40 Hertz. Let us make the frequency, firstly let us not have any phase difference. Okay, and if the frequency of xt is 40, let us make the frequency of yt as 80. Now let us see how this Lissajous figure starts looking. So I'm going to reset it. And you notice that the Lissajous figure is no longer circle or ellipse. It is now this 8-shaped figure. Now what is known from Lissajous figures is that if the frequency of xt is A and if frequency of yt is B, then A upon B is equal to the number of horizontal lobes divided by number of vertical lobes. So now how to find these number of lobes? To find vertical lobes, what you need is a horizontal line. Bring it close to the figure, like a tangent to the figure, and see how many points does this figure make contact with this tangent. So in this case, we can see that there are 2 points clearly, this and this. This is the number of vertical lobes. To find the number of horizontal lobes, bring in a vertical line and make it a tangent to the figure and see how many points, at how many points it makes contact. In this case it is 1. That is the number of horizontal lobes. Please note that this may be a little confusing because we are using a horizontal line, a horizontal tangent to see number of vertical lobes and a vertical tangent to see number of horizontal lobes. And you notice that we actually took A is to B as 1 is to 2. That means this is correct. Let us take another example. For instance, this time I'm going to make X to be of 80 Hertz and Y to be of 120 Hertz. Okay. Let us reset so that the Lissajous figure can redraw itself. So theoretically, what can we say about A upon B? A upon B is nothing but 80 upon 120, so 2 by 3, right? Let us see the number of vertical lobes. For vertical lobes, we need a horizontal tangent. We bring in a horizontal tangent. It touches the Lissajous figure at 3 points. So 3 vertical lobes. And bringing in a vertical tangent, it touches the Lissajous figure at 2 points. So there are 2 horizontal lobes. So this is how, just by looking at a Lissajous figure, you can give an estimate of what is the relationship between the two frequencies. Okay. Now, where is this used? In today's time, in the modern world, Lissajous figure may not have a very significant or widespread application. But why is this interesting is because in earlier days, when we did not have digital frequency meters, so we could not really measure the frequency of an incoming waveform exactly, right? And we also did not have phase lock loop, so we could not even measure phase of an incoming waveform very accurately. So what could be done in that case is that suppose we have an incoming waveform, say yt, and at the receiving end, they would generate a signal of a known frequency through an oscillator, put that on the CRO horizontal plates. So CRO used to have set of plates where you apply potential, so you could have like 2 sets of plates. You apply voltage across these and some other voltage across this, and then an electron beam would be coming, so it would be deflected based on the voltage. It would be deflected, and this beam would fall on a phosphorus screen and create color or light. Okay. That's how old TVs which work on CR cathode rays also work. So what they would do in that case is that, say, they generate a signal locally having a frequency of certain hertz, and they put the receiving signal being received on the y-axis, and then if they observe the xy plot, the Lissajous figure, that would give an idea of what is the ratio of the frequency of the incoming waveform with this. And as you see in the previous example, just by looking, if we do not know what is the exact phase of the incoming waveform, assuming they have the same frequency, by looking at a Lissajous figure, we could say what is the phase difference between the two waveforms. So if we were in an earlier time, suppose we were trying to tune a frequency to a particular value without having digital frequency meters, using a Lissajous figure, that would be possible. So in the lab, we would like you to try this out for different values of frequency. Some values are already given in the manual, which you should try out and try to validate whether this and this come out to be the same. I hope you have fun. Thank you.